Okay, so second speaker this afternoon, it's a pleasure to introduce Emad Heydari Beni. So Emad works as Nokia Bell Labs, but he also has a part-time position at our lab, and he will talk on zero-knowledge proofs and applications.
Yes, thanks for introduction. I don't like microphones, but I think we should talk with microphones because it's a big room. As Bart introduced me, my name is Emad. I'm part of Nokia Bell Labs. Bell Labs is the research arm of Nokia. In Bell Labs, we are doing many research, but in this area, an area of cryptography, we are working, or I would say applied cryptography, we are working on zero-knowledge proofs, homomorphic encryptions, and multi-party computation. We look more into the applications of these technologies. So this is another overview of me. It's me, if you cannot see me. But I'm also a postdoc at COSIC, but 20%. I also run another event, which is called Computing on Encrypted Data, Industry Days. So our goal is to transfer knowledge about homomorphic encryption, multi-party computation, and zero-knowledge proofs to the industry, and also bring companies that are active in this area together in the form of symposium that they can advance this area of research. But I'm a co-organizer in that event. If you're interested, just send me an email. I can invite you. It's an invitation-only event. So about zero-knowledge proofs, if I want to talk, we could have a course, COSIC course for a month. And we couldn't cover everything because this area is very new, but it's very active. Like every day, if you go to IACR website, if you refresh the page, there is a new paper, new proof system, new proof system. You will see a work from 2021 is considered to be old. And so, but I thought I'm going to give you some intuition that you understand what I understand from zero-knowledge proofs. That if you hear it, you know what it is, and you see one application of it. I mean, how it works as an application, but also a couple of applications. So let's start with the basics. Can you spot the cat in this picture? It's a mess. I mean, there's another example that people usually use, but I had to use a different one to be new. So you might find it, but you might not find it. But you want to convince me that you know where the cat is. I give you a Caesar, and I say that go to a room, crop this, and you show me the cat. You say, that's the cat, but I don't want to tell you where it is. So I can be convinced. I can say, okay, probably you know it. You know? You give me the cat, the paper is the same paper, and you know the cat. So there's a property called completeness. So if you know the coordinates, actually, you could crop the cat, right? And you could convince me. So that's a very informal way of defining completeness. So what is soundness? So if you didn't know the coordinates of the cat, you could try randomly, but it was very unlikely that you could convince me. So you wouldn't be able to convince me. And also zero knowledge, which means that you convince me that you know the location of the cat, but you didn't actually give me the coordinates. The coordinates I don't know, but I'm convinced kind of that you know the cat, where the cat is. So this is, I would say, zero knowledge in one slide. We can just say goodbye and go right now, and it's over. But that's just, I wish it was only this. It's not just this. So one of the very core primitive protocols of this is interactive protocols, interactive proofs, that Alice sends a commitment to Bob, and Bob challenges him, and then Alice provides a proof, and Bob verifies the proof. This is like, I would say, the foundation of this type of protocols, and there are so many variations of this. So if we go back to our example, Alice claims that I know the coordinate of the cat, of a cat. And then I told you, and then Bob tells her, so prove it to me, right? And Alice cropped the picture, cropped the cat, and sent it to Bob, and Bob verifies this with different methods. I don't know. It checks the claim, checks the proof, checks the quality of the paper to see it's the same, whatever, and then rejects or accepts. So again, if we want to be more general, so completeness is when if the prover is honest, so the honest verifier always accepts the proof. And soundness, I have my water, I'm a bit sick, sorry. Soundness is that if the claim statement is not true, the verifier rejects the proof Oh, I mean, rejects the proof, yes. And that's a protection against a malicious prover. And there's another concept called special soundness, or knowledge, proof of knowledge soundness, is that if the prover doesn't know the secret information, which is called also witness, that secret information associated with a public statement, the verifier cannot be convinced. So this is a bit more specific. So it's a proof of knowledge that Alice knew that coordinate that could claim that thing. You can think of it like that. But there's a very famous old protocol by Schnorr, which is the foundation of most of zero-knowledge proof systems. I'm going through this one more time. I mean, for the first time, of course, not one more time. So Alice wants to prove that she knows W or omega W, so that she could create X, but G power of W is X, and X is a public statement. But because of discrete log, there's a problem with cryptography. Most of you are cryptographers, but many not. So if you have G power of W, or if you have X, you don't know what W is. So we cannot solve this problem. It's a hard problem. So Alice generates a random value R. By the way, I'm following the same interactive proof in the previous slide, but a bit more details about the protocol. So Alice generates this random value R, computes A, like G power of R, and sends this A as a sort of commitment to Bob. And Bob, what it does is that it generates a random challenge, and challenge Alice, send the challenge to Alice. And Alice creates this, creates a Z, which is Z is R plus C times W. So Alice could do that because Alice knows W. And then Alice sends Z to Bob, and Bob runs this. And if this works, I'm going to show you why, but if this works, Bob is convinced that Alice knows W because she couldn't prepare this Z for him. And the completeness is as follows. So we have G power of Z. So Z was R plus C times W, right? So this is equal to G power of R, because A is G power of R, right? We had it in the commitment, in the first communication. And G power of G to the W is X. We replace that. And if you do the simple math, the high school math, this is correct. And Bob is convinced that she could come up with this Z, and she knew W. So the special soundness, I can show you how the special soundness is satisfied. So if someone, just forget this, if someone knows the truth, knows a secret, like for example, you know a secret, there is a way to ask you the secret. I can either politely ask you the secret, or I can torture you, I can beg you, but I know there's a secret. But if there's a secret, I can somehow extract it from you. But mathematicians also, they have this concept called extraction. So if Alice really knows a secret, W, we should be able to extract it. We should rewind, we should play with the protocol, we should somehow be able to extract it. If you cannot extract it, Alice doesn't know it. And that's also zero knowledge. Because of zero knowledge, we don't see it in the protocol, but we should be able to do that. So imagine we have these two tuples. These two tuples are valid execution of this protocol. If you look at the views, we have A, C, Z, and we have A, C1, and Z1. Forget how it is constructed, but this is a valid view of this protocol, two different instances. So what we do is as follows. If G power of Z1 divided by, we divide this G power of G to the Z1 and G to the Z2. I know I study mathematics in my own language. Speaking in English is really tough. And then we do the same on the right side, right-hand side. We do A times X power of C1 and A times power of C2 divided by that. So A, you can cancel A, and we have X power of C1, we have X power of C2, or we can calculate that. And if you compute this, we can somehow extract W. So there was a W. So this is a special sound, this protocol. But How sound is this? So we had to choose, actually, the verifier there had to choose C, which was randomly, but the domain of C is 0 or 1. So basically, type 2 values only. So what if Alice fakes it? Alice just say that it's likely that C can be 0, right? And Alice doesn't, imagine Alice doesn't know W. Can do this, right? So if she picks C equal to 0, it's a she. You know, she's that much chance that she can succeed the protocol because it could be 0, right? It could, and then Bob will check this and it works, right? So this is not really, the soundness is not very good in this protocol. So what we can do? We can do two things. We can repeat this protocol many times, then we have many Cs, then we have more trust in the soundness and we have better soundness, or we can choose C randomly. I mean, the verifier can choose C randomly from a bigger domain, from, I don't know, 256 bits of numbers, you know, like numbers with from that domain. So it's bigger, and then we have better soundness. There are two ways to do that. So soundness is really important. The larger, more soundness we have, the larger domain is that, or the more communications we have. So, but today I'm not going to talk about zero-knowledge proofs all the time, so I would like to talk about ZK-SNARKs as well. What if we wanted to prove complex statements, like a software program, a very complex program with a lot of statements? How we could do that, a general purpose program. So maybe first we should talk about pre-processing argument system. Because what we have seen so far was the argument system, very simple Schnorr protocol that you just run these interactive proofs. But in the pre-processing argument system, there's a setup time. In the setup time, we give the circuit. We give circuit is the program that we want to prove. We give the circuit to the setup time, to the setup process, and the setup process generates some public parameters. Some public parameters for verification, and some public parameters for proving. So if you want to prove something, we use these public parameters. Think of it as a public key, and we use verification key when we want to verify that. I will show you with an example, very famous example from Vitalik Buterin, the founder of Ethereum. He has a famous blog post, From Zero to Hero. I've grabbed that example here that I can show you how we can use this, how we can generate those. And the second protocol, second part is proving. So you have this public proof, you have this proving key, and also your public statement that we had in the previous slide, and also a witness, like for example, the coordinates of the cat, or it can be an input, private input to a program that you want to execute you want to prove the correct execution of that program. So this is the input to this proving system, and output is, of course, output of the program, as well as, or maybe not, but as well as the proof that you can verify. And the verification algorithm, the verification process takes this proving key, verification key, and the public statement, and the proof, and can tell you accept or reject. This is a picturesque way of showing it, as you can see. So what is a SNARK? A SNARK means that succinct, non-interactive argument of knowledge. I dropped the non-interactiveness because I'm not planning to explain it today. But S, succinct, a big word, which means proof is short. So how big program you have, the proof has to be short. And by short, there's a definition there. It means that it's logarithmic to the size of the circuits you have, the size of your program. And also the time to verify has to be logarithmic to the size of the circuit or to the size of your statement. Because the statement, you have to read the statement, right, to be able to prove it. And that time, it takes time to read that. How big is that? I don't know. So this means it's succinct. So it's small, the proof is small, and also the verification is very fast. Okay, so what the department head at Bell Labs always says you should learn it by doing it. Marcus Hoffman, I think Tom also knows him. So I thought it's better to do it together and we can learn what I meant, what I explained, because it was maybe very vague. What was this SNARK? So, but SNARK, if you want to apply it also to computation, you cannot do it directly to a program. You have to transform this to some shapes, some forms, some encodings. Then from there, you can take it and do the processes. So we have to first convert the problem to a right form. So what we do is that we do the computation, we write the program in an algebraic circuit, and then we convert this to R1CS, is one of the famous encodings. There are many more, like Plonkish, CCS today, CCS, Plonkish, AIR, many. But R1CS is one of the first ones, so I picked that one to choose. And also we convert this to CAP, to a quadratic form, and then from there we will see how we can generate the very short proof and how we can verify this fast. So the goal is this. This is an example. So the goal is that, imagine we have this equation there, and we want to prove that we know, we want to prove the correct execution of this equation if we input x equal to 3. And that 3 can be secret or can be a public thing. We want to compute this and say we know the value. But this could be a more complex program, just a basic program. So if you write it as a program, it can be this, Python code. It can be evaluate this, could be anything. So the first step to move towards to R1CS is to flatten this code. So you write this code in this form. So on the right-hand side, on the left-hand side has to be a variable. On the right-hand side has to be at least maximum 1 multiplication or nothing or many additions. This is the format. You can see this equivalent program, just make it more complex unnecessarily. But there are compilers today that you can compile it for you to this format. You just write main code and compile. And that's the circuit. If you would be crazy and write in a circuit, it would be like that. So there are gates. There's multiplication gates, 2x. You can read it, it's very simple. That second evaluate function, you can see that's a circuit. So we have multiplication and addition gates. And there's outputs, inputs, and the wiring in between, right? What time is it? Okay, I don't have time. Okay. So we have 4 gates, 5 variables, and 1 constant with the value of 5. We can see it there. So let's encode this to R1CS. So R1CS is composed of 3 matrices, giant matrices. The size is dependent on the size of the program you have. It can be very huge. I've seen matrices of a couple of million gates, so it means that they had million rows. And I think Ligero is a proof system recently, and they did a test with the Llama model. So they wanted to prove that that execution of a Llama model is correct. So they had, I think, in the order of billions constraints, which means that billion rows. That's crazy. I will come back to that, why this is like that, and what we should do about it. So there's A, B, C. This is these matrices. I will explain what these things are. So A is, some people call it left, B, right, and C, out. So think of a gate. Gate has a left-hand side, right-hand side as input, and 1 output, right? It's something like that. And S is an instance to this circuit. It's all the wire values. You will see right now. I'm going deep into this step by step. So S, let's have an agreement that S is this format. 1 represents any constant we have in this circuit. For example, 5, we will come back to that. X is the inputs, out is the outputs, and the variables. These variables or values are the circuits in the middle, the wires in the middle in the circuits. I'm going slow that you see what's going on. So as I said, I is left, B is right, and C is output. So I want to populate this in this matrix. And on top, you see the columns. So I want to, 1 is for this column, X is for this column, output is for this column. So let's take the first gate on the bottom. So we have 2 input X, right? So we have X on the left, X on the right. You can see everything is 0, but 1 is for X. And output, where 1 is 1. It's clear, right? So we do the same for the second gate, but I messed up the left and right here. So var1, I assume is left. I saw it a few minutes ago. And then I think the picture, you could think of it like that, but then it would work. So on the right side, which is x, we have x. On the left, which is, and C is var2. You populate the second row. The second row would be the second gate. The third gate. The third gate is special because it's addition. R1CS has a special treatment for addition, so you can have many of them in one row, for example. So if you see here, we have x, which is the input, and var2, and then we say this is a constant. It's like a constant. It treats it like a constant. And then the output is, I think, output is var3. I think that's a typo. There's 1, 0 there. There's a 1 extra 1 there. But it doesn't matter. So the last gate is 5. 5 comes here. 5, we pick the 1, because we said that's reserved for constants. And var3 is addition gate. You can have it here. Okay. And then we have this and the output. Yeah. This is a copy-paste issue. This should be, the out should be 1, the rest should be 0. But you can imagine. This is the encoding. So we have this program. There are compilers today. You don't need to do that. But some people do, for some reason. I don't know why. There are compilers. You can compile your program to this. You will never see that. If you use GCC also, you compile, you don't open the binary. You can look at it, but you don't do that. Some people do still, but. So this is an instance. So instance means like that vector there. So it means that if you input x as 3, which we had on top, if you execute this, all the intermediate values on the wires will be this: 1, 3, 35, 9, 29, 27, and 30. If you compute it, you will see. You don't have to do it. Any questions so far? Okay. So I just moved everything up. Nothing happened. Okay. So we had that formula for R1CS, AS dot BS minus CS. And the dot in the middle is Hadamard product, means element-wise. And the dot AS is like a dot product, like a matrix vector multiplication. You multiply. So let's test something together. Let's grab this row, which is the last row. Let's grab this and multiply that. But there's a typo. The typo comes around, but this comes from external source. So I'm applying that formula from R1CS to this. So we have this 5. I wrote it in transpose. And we have one instance, which was exactly that, 1, 3, 35, 9, 27, and 30. If you do a dot product or inner product, and then you do the same for the second 2 vectors, and the last one, if you do this, is 0. And if you do this for all rows, it's 0, because this is how the encoding works. So basically, it means that you did it correctly. Computation, this instance, this computation trace that you have from all the wire values actually satisfies this circuit. So it's correct execution. But still, this is huge if you want to give it to a verifier. This is like, it's easier if they compute it themselves. So we need to make it very small. But don't forget that, as I said, the length of this matrix can have many rows, millions to billions. Yeah, so it's not easy. This is a very simplified program. So let's take it from here and create polynomials. So cryptographers cannot deal with this. They have to deal with polynomials. They love polynomials. So they are going to interpolate, for cryptographers, they're going to interpolate column-wise 18 polynomials for all this. So I'm going to say, wow, if you're not a cryptographer. So what they do is that they grab this column, first column, as an example. They come up from some numbers, 1, 2, 3, 4, 5, 6. whatever, 1, 2, 3, 4, and they have this. We can do interpolation, like Lagrange interpolation, and we can come up with a polynomial. And that means that all these points, if you evaluate them, this is 0, because this polynomial actually passes through these points. You can put it in MATLAB, or I don't know, Sage or Python, interpolate, and interpolates. Which one? Yeah. Should be 5. It's 5. It's a typo again. I had short notice for this talk, so I had to do it quick. It is 5, that one. Let's fix it right now. The errors are adding up. Yeah, I know, but stop it. Okay. So now imagine we do this for all columns. We have that many polynomials. There are around 18 of them. So we have so many polynomials. But this, what is this? This is exactly this R1CS, but on the polynomials. So I'm doing this dot product between the instance, which is a vector of values, with the polynomials. But I wrote in a fancy way with a fancy notation. It's the same thing you saw for one line. Is it clear? Cool. Well, the same. Yeah, actually this is correct. Yeah, because for point 1, this should be 0. If it's not 0, then the computation was wrong, actually. No? Good. The system is sound. So these clouds are for yourself to have some imagination. What would be? What would it be? So that's the px, the polynomial p that we created. So we have these points. We can create another polynomials because we are cryptographers. So we have this t, we have this polynomial, and this polynomial, if you evaluate it with 1, 2, 3, 4, it's going to be 0, right? Or for any other thing, we don't care. You agree that p is divisible by t? True? It's true, right? Because if you put these points on it, this polynomial is going to be 0. So it's divisible. Simple, no reaction. So perfect. So if you divide it, you will get another polynomial plus a remainder, which is 0. Right? I get reactions. Good. So we can write this like that also. We can say that p is equal to some polynomial, but we don't know what it is, times t. We don't know what it is because if we have p and t, we can know it, right? That's the formula there. We will come back to that. We just want to create this process of checking as succinct and small and small and small as possible, and also fast to verify. That's why we are doing these things. You will see why. I'm going to confuse you even more. So if you go back to preprocessing argument system, we had 3 algorithms, 3 process or 3 protocols: setup, proof, and verify. The setup, it takes a function and outputs a proving key and also a verification key, right? That you use the proving key, which is called evaluation key, I guess. But this comes from paper of Pinocchio, by the way. It's not in the blog post. It's one of the first papers that they present a practical system for verifiable computation. I mean, the whole compiler, machinery, the pipeline, everything they explained. So from here, we had a takeoff for this domain. So what we do is that we generate the cap for the functions. We had these polynomials, right? But also, to generate this, we didn't need to have the instance. We didn't have to have the execution of a polynomial. To check this is consistent, we needed to add the s to see it's consistent or not. But to generate this, we didn't need to have it. So we have t, which we saw, we have those polynomials. We don't need to remember why, how, where, because you might forget it, but we have it. So we pick a random number, r, and we come up with this. So G, we come up with the evaluation of all these polynomials at this random point. And no one knows the point. We throw away the point, the random R. In the setup time, we create this R, we come up with this. So G power of A1R to A16. They're separate values. You have them separately. And also you keep a track of this, the powers of R. This comes back in a lot of proof systems and commitment systems. So this is we called proving key, which we will see how we're going to use it. And this is verification key. And the verification key is G power of evaluation of R on polynomial T, that T. We use this for verification. Simple. So let's prove. So we have this key, proving key, we have the public statement and the witness. But I am simplifying a lot, so I'm not using the public statement. I'm just trying to show you with the previous example here. So what we do is that we run the function, we execute it. We call this witness generation. So you generate all the values on the wires, the instance, the S instance, right? We had like one, those input, output, and variables. You compute this. So what is this? So you want to compute somehow homomorphically or blindly, because everything is happening in the exponents. You want to calculate the evaluation of A, B, C at random point R. But you're creating something that you want to give to verifier later, but you don't want to give the polynomials to the verifier directly, right? Because it's your function, and he might find your secret. So that's why you put them in exponents, and because of discrete log, they cannot figure this out. So what they do is this. We have, from the public parameters, we have A1R, B1R, the evaluation of R at B, and evaluation of R at C, and everything. We have everything here. You just multiply them, and each of them separately also power of your instance for that slot, for that element. So that SI comes in, and it's actually similar to that formula on top, the PX. You can see the P polynomial P. That's happening on the exponent. So you calculate that for A, B, and C. It's clear? Hopefully. Simple. So we need to find that polynomial H. Do you remember that we had this, that P was divisible by T, so we divide it, and it gives you a polynomial, something, which has, so what you get in fact is the coefficients of this polynomial, which is H1 to H something, like the order of the polynomial. So we have all the value H, and you know the polynomial. This is how I wrote the polynomial with the sigma. So we want also the evaluation at random point R for this polynomial. Because we are constructing our proof, you will see why I'm doing this. So this is exactly that. So we have the last line here, G power of R1, R6. So if you evaluate H at point R, it will be your coefficient, this is 0, H0 plus H1, X, but X you replace it with R, right? And then H2, X power of 2, which will be R power of 2, like that. So we can write it also like this, that this will come to the exponent. Everything happens in the exponent of this. So we have that. This is a proof, actually. It's R, yes, I wrote H. Yeah, it's a mistake. That's very correct. R. Yeah, yes, this is R, yeah. Let's fix this again. So many things. I had to write LaTeX in the PowerPoint. That's a different beast. Good? Perfect? Okay. So we have this proof. The proof is 4 group elements or field elements, right? It's very short. So whatever computation we had, millions of rows in that matrix, is boiled down to 4 group elements. So this is short. This is like a, I would say, succinct. So you always have this particular size, and your group has a certain size, and it's very short. There's even a smaller than this. With grad 16, you can have 3 elements, if I'm right. And how to verify that? This is easy, used by linear pairing. I'm not going to explain it here, because I thought that's a separate lecture. So you somehow check this relation in bilinear pairing. And what is this relation? Look at top. It's exactly that. You have P, which is an R1CS relation. AB minus C equal to HT, which is on the right side. P is equal to that. You can do 3 pairings. First pairing divided by another pairing equal to another pairing. And magically, this pairings will check this relation. That's some cryptography bit here I'm missing, but I'm not writing it down. But it is possible with some functions, with 3 times calling it, to check this relation that is held. So verification is also super fast. For 3 pairings is quite fast and running, checking all the correctness of every row for 1,000,000 rows and to make sure that the instance is correct. So I conclude the verification here. Was everything clear? Any question? Good? Yeah, okay. But if you don't get it also, you can use a lot of software today, something like Circum, Socrates, Noah, Cairo, many. And you can just write some domain-specific language or Rust or Python, and they convert this to, you compile and it gives you proof. Another proof, it gives you code that you can give input, and then you can have an output and proof. And there's a verifiable code that verifies this if you're building software. This is what we're doing a lot at Bell Labs, solving different problems, because you can now actually execute something and generate a proof that the proof can verify that the execution was done correctly. It's huge, a very powerful primitive. So what happened if the input data is huge? Or what if the input data is a stream? So imagine the huge input data, so the matrix would explode, I think. So it's like, imagine you're training a data set. Data set is 2 petabytes. It just doesn't scale, this approach, right? So what would we do? So we process data in the batches and generate proof per batch and verify proof recursively. So first batch, I generate the proof. At second batch, I generate the proof. I check this proof in my proof generation, and recursively I'm doing this. I have a picture for that. So imagine this is a big data set on top, that's a big tape of data. So chunk, batches, I feed into the first prover instance. Prover, I mean that is a circuit that is running this software that you're going to generate the proof. It outputs actually execution. Imagine this is 3 trillion records, they want to calculate an average. So you have a running average going, and then you have to calculate it to the end. But the function is the same always. You generate the output and a proof. And the prover, next execution of the prover takes the output and the proof, but this time inside the proving circuit, inside the circuit, it also verifies the proof. So if it verifies the proof in a provable way, it doesn't need to prove it again. So just generate a proof for this execution and continues. It's a bit metaphysical, but in the end, you have, again, like the previous proof, you can have 4 group elements for very large data sets. But this is a very active research topic. I'm explaining this from now on. I'm talking about applications and also the current research threads that people are working on a lot in academia and also industry. This is a field very active in industry as well. And they do research, people. So there is a new track that started in 2021, recursive proofs called NOVA. So they took this idea, but actually inside they don't do a SNARK verification. What they do is some sort of lightweight verification. So you prove first chunk of data, you generate the compute, you generate the proof, you verify that very efficiently with checking some hashes and things like that. Things like blockchain, for example, it's a chain of hash. You verify this, and there's a commitment. I don't want to explain the details. It requires a separate lecture, but it goes to the end. In the end, it gives it a general purpose SNARK, like what we had in the previous slide, and generates a proof that you can actually, this is a breakthrough, I would say, in my opinion. But this was a line of work. After that, we had Supernova. And what Supernova did was that this Innova prover has to run the same function. If you wanted to calculate the running average, for example, it has to be average function. With Supernova, actually, you can have different functions. It allowed people to create zero-knowledge virtual machines, which I will talk later. And then, with Protostar, they advanced the field. With Sangria, they tried the same ideas on a different proof system called Planck. And with Latticefold, we come up with the entire Nova again, but with different cryptographic assumptions and primitives like lattice-based cryptography. And this system then it's post-quantum. And with Hypernova, they optimize this verification drastically. And it's published just a few weeks ago. Yeah. But this zero knowledge also has application in machine learning. People always think it's about privacy, but that's not true. What people are looking into, but I don't think there are a lot of results, but people are actively looking into, is ZK-ML. So what if you have a training software that is training, is being trained but with some data, you want to generate a proof of training for your customer. Why? Depends on the application, but people are looking into that. Or you want to also prove that this model was trained with particular data. We can use these techniques to generate a proof of training for exactly particular data and not that data. Because maybe some data has license and your business don't want to use those data because there's that company that they are offering the model, they're abusing and using some data that they didn't have license to use. Or proof of correct inference. Think like in some mission critical application, then you need to have really model inference with accuracy. And some companies sell you a model, then you query, but for them, in order to save costs, they're going to use a light version of that model, not the same model that they promised to you. Because that model probably, every now and then they switch the model. But then you don't know. But with this system, you can have a proof of inference. I'm not diving deep into the application because it's not my area, but I know people are working on this big time. Really, it's a huge topic. Another thing, so if you want to run a ZK prover, Polygon, first of all, what is Polygon? Polygon is one of the well-known blockchain projects. So they have zero-knowledge system for roll-ups, whatever roll-up is, which is actually very relevant, I'm not explaining. So they say that the system requirement is 1 terabyte of RAM. So go figure. So I think basically very few people maybe can run such a prover node. It's because of all those rows that I talked to you about. They're extremely memory intensive and also compute intensive to do them, use parallelization because they're highly parallelizable, by the way. So this is crazy. So what people are doing right now, there's a line of research that people are looking to proof outsourcing. Or in other words, you delegate the construction of proof to someone else. And it all started with the work DI-ZCAT. In this work, they use cluster computing and I think they use GROT16 proof system, and they could outsource the proof construction to this highly scalable system that it could accelerate tremendously and then send them back the proof. The prover had the proof, and she could use it. But what they didn't care is that when you send the computation trace, all the wire values, actually your secret is there. There might be a lot of problems, so they didn't care about privacy. Actually, it's really important. I would say not just privacy, it's confidentiality also. So there's a new thread of research started working on MPC, secure multi-party computation, and homomorphic encryption, how we can outsource this using these technologies. Like it started from the work of Rahimi et al. In 2021. You can see now what I said. 2021 is considered very old, to be really old in this domain. I'm working on this track myself. For me, that's like ancient. And then Alex Ozdemir and Bonnet, they also come up with a system similar to Rahimi. And it is based on MPC. So you secret share, somehow you break your computation trace, that S vector, into several pieces and send it to each piece to several different parties. And they collaboratively, they cannot see your computation trace, but they collaboratively can, in fact, compute a proof for you and send it back to you. You can reconstruct the proof. And they have really interesting results. And the same, Alessandro Chiesa et al. And ZK-SNARK, they have the same flavor of approach, but from GGW and GGW started actually using homomorphic encryption for doing that. We are looking into that ourselves. And the last work that I put there is Pianist in the Oakland conference this year, security and privacy, IEEE security and privacy. And in this work, they didn't care that much about privacy, if I'm right. They come up with a proof system that is horizontally scalable, that you outsource it, but you can speed up by adding extra nodes. In the past, it was not possible. It's one of the first ones, and I know from some people that also some people in the US, they come up with a horizontally scalable GROT 16, which is really awesome. It's coming. It's under submission. So another threat that people are working on is virtual machines. So what if we could have a virtual machine, an instruction set, that you could compute any program, and it would give you output and a proof. That's a holy grail, I would say. So there are a couple of companies working on this, like RISC-0, Nexus VM, Triton VM, many Ethereum virtual machines, many of them, like Polygon Maiden, many, Aleo. So this is a big topic as well. So what's going on here is this. So you have an instruction set like RISC-V or WASM or 8086 if you're crazy. So you can write a circuit for that, like what we did before, like that R1CS. What is another R1CS? Like you can write a circuit. Think R1CS. And then your program, in fact, this time is the input to the circuit. Last time in the program, actually the input was the value, right? So what is the program? The program is that when you give it to a RISC-V, you said that run these instructions in this order. Run, I don't know, move, insert, read, copy this, that. So basically, your program is telling the circuit which instruction to execute. So basically, your program is an input to the circuit. And then you have to deal with the registers and memory as well. Because these instructions, they might read from memory, they might edit the memory, they might put something in the registers. But all the time, you have to make those things also consistent and keep a trace of them. And eventually, you can generate a proof and also program output. This is usable today, especially with RISC-0. You can write program in Rust, and in the outputs, really proof. We have a lot of prototypes at Bell Labs. And Nexus VM is also doing a very great job. I think it's a company to look into and invest, if you can invest, I don't know. I believe they have a dream team. They have very famous cryptographers there, and yeah, this is going on. This is a very active topic, and so at Bell Labs, we are working on this subject as well. So another very cool application is fighting disinformation. You see this picture. You see, wow, it's bad people, right? This is actually the complete picture. Someone is giving water to the soldier, but there is still gun. But another media show you this. It's totally different things, right? So there's a line of work that people are working on fighting with this, against disinformation with zero-knowledge proofs. I was surprised when I saw it for the first time, but it's possible. I will explain how. How much time do I have? I don't know. 8 minutes, good. Good, perfect. So, how we can prove that if you see a picture on the media, it can give you a proof of provenance, content provenance, that it comes from a camera. Really, on that location, they took a picture, and you are seeing this, and what happened to that picture on the way. And then you can see what happened, and you can then rely on your own judgment. But this is an active topic. So, Sony, according to C2PA standard, they hard code a signing key in every cameras right now, the new models, I think. So when you take a picture, what it does is that It takes a picture, of course, first thing. And there's metadata about location, timestamp, where the camera is. It creates a signature with this information. Put the signature next to the picture. So if you have the picture and metadata, you can verify the signature. But then if you send it to a browser or anywhere else, now browsers also implementing this, you can verify the signature. So that you are sure this comes from a Sony camera. The picture, if you flip one bit, the signature doesn't verify. So you know it's original picture. But is it really usable? This question. Because if you're a news agency, or if you're a photographer, you always change the brightness a little, crop a little. It's like I'm talking and there's some, I don't know, this water pipe there. It's not professional. You want to just cut this, right? So there's certain addition and modifications allowed in this area. I mean, professionally in journalism, they're allowed. Like you can, maybe the picture is colorful, you can make it black and white, or crop it 1 centimeter, a little. I don't know the operations. I don't know those. But if you apply any of them, or even sometimes the pictures are a couple of gigabytes or megabytes, they reduce them to 1 or 2 megabytes because they want to load it on the phone. And that already destroyed the signature. You cannot verify. So there is a line of work with zero-knowledge proofs to do this. So what they do is that the picture is taken by camera with the signature. I made it small, but normally it's very big. So you give it to the SNARK. We're cryptographers, we love it. We give it to SNARK. So first, we verify the signature in the SNARK. So whatever happens here is verifiable. Whatever you do here, it's with this R1CS, these matrices, and blah, 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 blah. So you can verify what happens there. So you first verify the signature. That shows that, okay, the picture was correct. You apply the modification, for example, change the brightness a little. You have a new picture, green. And then you verify that this operation, this modification was in the list of allowed operations. By the way, this circuit is open source. Everyone can see this. And then you check that the metadata of the previous picture and the new picture are the same. So location, timestamp, everything's the same. And then you return a picture. So what it gives you is a picture and a proof this time. But this proof, in fact, if you verify it, this is a SNARK proof. If you verify it, it also gives you the guarantee that the picture comes from an original version of it, from a Sony camera, and the picture is not forged, and the allowed modifications were done. Location, timestamp, and metadata are the same. This is line of work. The people are working. It started from ZK-Image in 2022. Again, 2022 is old in this area. It's so active. I didn't write down everything. And then Dan Bonnet and Trisha Dutta in Real World Crypto, they show a technique to make this verification faster, because the image can be 12 megapixel or even more. This circuit would take days to compute, not seconds. So they managed to make it like 4 minutes, something like that. And then this year, Real World Crypto, they introduced new techniques to make this even faster, or in a different way. I don't think faster, but different way. And it's very cool. In fact, there's a wide deployment in Rolling Stone, which you don't see. I see myself here. Let me bring it here. So I contacted Trisha. She's a friend. I wanted to see where are the proofs. I couldn't find them, but I could find the proofs, C2PA proofs. But you will see right now. So if you scroll down, I think this should be the future of journalism, in my opinion. You see a picture. It's from a war in somewhere in Europe. Yeah. Then there is this sign here. You click on this, then you see the entire history of this picture. So you can go down. You can see certificates. This picture is on Avalanche and other blockchains, on IPFS, the actual file. But this is what we care. You can see the additions, the crop and resize, sharpen without a Photoshop, authenticated, a scan, blah, blah, blah. And then you can see this. You can just click on it and see the signature and what is used, and you can verify that. This is really amazing, in my opinion. If my opinion matters, but... So what's going on, what people are working on today in this community of zero-knowledge proofs and SNARKs. So people are looking at SNARKs with the smaller fields, I mean, mathematical fields, because they're better for hardware. Now, most of the SNARKs are based on elliptic curves, and they're really, each value you saw is like 256 bits, and this is not really easily translatable to hardware. So people are looking at smaller fields also because of hash functions, because hash functions and also encryption functions like AES, SHA, they do a lot of bitwise operations that it is hard if you have a 256-bit number. So there are a lot of research going on there, and also recursive and iterative SNARKs that I talked about. And there's a very active research also on post-quantum protocols based on lattices. And also people are looking again at basic primitives like sum check protocols. Again, it was very popular in the past, but again, they're popular because they're really faster and very powerful primitives. And lots of papers are published here, being published, and also ZK virtual machines. Everyone is looking into memory consistency, for example. The memory consistency is very slow. They're improving that area big time also, especially Nexus VM. And ZK machine learning is one of the largest topics in this area. And the holy grail, as always, is verifiability for homomorphic encryption, which is a still open problem. If you want to say that a fast one is open problem, but slow ones are available, published by our own research group here. Yeah, that's my talk. I put some sources where I found my information you can find later, and thank you very much.